Hello everybody. In this video we'll be covering one of the sections from chapter 8 of our text entitled Quantities and Chemical Reactions. In this video we will be covering stoichiometry. So the amount of every substance used and made in a chemical reaction is related to the amounts of all the other substances in the reaction. And we've seen this to be true in two ways already. We've seen the law of conservation of mass, that we have to have the same number of atoms on either side of our reaction, and we were able to balance the reactions by making sure that we hold to this law of conservation of mass. Now we know that there's a certain ratios that the molecules and atoms are going to combine in. The study of the numerical relationship between chemical quantities in a chemical reaction is called stoichiometry. So I think one of the easiest ways to think about stoichiometry is in the context of cooking. So I want you guys to imagine for a second that the number of pancakes you can make depends on the amount of ingredients that you use. So 1 cup of flour, 2 eggs, and a half a teaspoon of baking powder is going to make 5 pancakes. Okay, so we have a recipe, and certain ratios are going to yield a certain amount. One way that we can express this mathematically is by using these 3 slashes right here, and that means like defined as or requires. It's related to each other. So we don't always want to make 5 pancakes, right? So if you want to make more or less than 5 pancakes, you can use the number of eggs you have to determine the number of pancakes that you can make, right? So if I have a certain number of eggs and I have more than enough flour and baking powder, I can figure out how many pancakes I can make if I use up all my eggs. And the way we're going to do that is by making another little conversion factor here, like the ones that we've been using so far. So we know that 5 pancakes requires 2 eggs, so I get 5 pancakes per every 2 eggs. If I have 8 eggs, I can do this math out here, and I can see that 8 eggs is going to make 20 pancakes. I have 4 times as many eggs, I get 4 times as many pancakes. So the balanced equation is the recipe for a chemical reaction. For instance, if we had this chemical reaction here, 3 hydrogen molecules plus 1 nitrogen molecule is going to make 2 ammonia molecules. This is telling us that 3 molecules of H3 is going to react exactly with 1 molecule of N2 and make exactly 2 molecules of ammonia. Since we count molecules by moles, it's also equivalent to say that this is all true for the number of moles. Okay, so 3 moles of hydrogen plus 1 mole of nitrogen is going to make 2 moles of ammonia. So since we know that, let's take a look at an example here. So what if I asked you how many moles of NaCl result from the complete reaction of 3.4 moles of chlorine gas? So I am going to put the caveat on here. We're going to learn later. Part of the trick to this is that we're saying the complete reaction. Okay, that assumes that we have more than enough sodium. All right, so the only thing that we're thinking about limiting this is the amount of chlorine gas. So what information are we given? We're only given that we have 3.4 moles of chlorine gas and in a chemical reaction. We're asked to find the moles of sodium chloride. So our solution map here is going to be to go from the moles of chlorine gas to the moles of sodium chloride. What we need to know is what the relationship between those two are. Okay, so we have this presumed 1 right here, and we know that that's going to produce 2 of the sodium chlorides. So our relationship is that for every 1 mole of chlorine gas consumed, we're going to make 2 moles of sodium chloride. Again, we're going to pay attention to how we put these into our equations. Okay, so we have the 2 moles of sodium chloride because that's what we want our answer to have the units of, moles of sodium chloride. We're going to put the 1 mole of chlorine gas in the denominator because that's what we're given and that's the unit that we want to get rid of. We go ahead and multiply by our conversion factor, and we'll see that we cancel our moles of chlorine gas, and we get that we would wind up with 6.8 moles of sodium chloride. And since the reaction makes 2 moles, so the relationship is 1 to 2, and we're generating twice as many moles of sodium chloride, this number makes sense. So let's try another practice one. According to the following equation, how many moles of water are made in the combustion of 0.1 moles of glucose? So we're given this reaction here. We have our glucose. We're adding oxygen to it because it's a combustion reaction. And we're going to generate 6 moles of CO2 and 6 moles of water. So we are given our 0.10 moles of glucose, and we're asked to find the moles of water. We need to take a look at the reactant or the chemical formula here, and we need to see that for every 1 mole of glucose we're going to produce 6 moles of water. Therefore, we can write this statement down. We can use that to convert between the moles of glucose and the moles of water by including this conversion factor here. When we apply our conversion factor, we see that we produce 0.6 moles of water and that our moles of glucose are going to cancel. We do our little check here. And since there are 6 times, right, our relationship was 1 to 6, we're getting 6 times the number of moles out, then this number does make sense. So we know that there is a relationship between the mass and the number of moles of a chemical. And the molar mass of chemicals in the reaction and the balanced chemical equation allow us to convert from any amount of chemical in the reaction to any amount of any other. Okay? So basically, we don't typically measure moles. We were going to measure mass in the lab. But we now have the tools to go from the mass of one of our reagents to the moles of that. We can use what we just learned to figure out the moles of another portion of the chemical reaction, and then convert that back over to mass, which is again something that we can measure. So let's think about that. So if we take photosynthesis, for example, right? Remember, we're producing a carbohydrate, so we're going to take carbon and we're going to hydrate it. The relationship for the reaction gives the mole relationships between the amount of glucose and CO2, but we need to know the mass relationship. So the solution map will be, we're going to go from the grams of CO2, right, because that's what we're being given in the problem here. So we're solving the problem. How many grams of glucose can be synthesized from 58.5 grams of CO2 in photosynthesis? We're getting the mass of CO2. We can find the moles of CO2, use that to find the moles of glucose, and then finally the mass of glucose. So let's take a look at what that looks like. So we're being given the 58.5 grams of CO2, and we're being asked to find the mass in grams of glucose. We have our solution map here. We're going to go from mass of CO2, moles of glucose, mass of glucose. And we have to get all of our relationships, right? Remember that we're going to go to our periodic table and we're going to add up the atomic masses for each of these different elements to find its overall formula mass. We're going to do the same thing for CO2. and then we're going to look at the chemical reaction to find the relationship between the moles of glucose and the moles of CO2. And we know that for every 6 moles of CO2 we consume, we're going to produce 1 mole of glucose. We can then make a different conversion factor for each one of our steps here. And remembering to put the unit that we want to cancel in the denominator and put the unit that we want in the numerator for each one of these different relationships. When we string it all together, we have the grams of CO2 that we're first going to cancel. We're now in moles of CO2. Then we're going to come over here. Now we're going to have moles of glucose. And finally, we'll have the mass of glucose here. And we see that we produce 39.9 grams of glucose from the 58.5 grams of CO2. So since 6 times of the CO2 is required in order to produce the glucose, but the molar mass of glucose is only 4 times that of CO2, the number makes sense. So now, because we have multiple steps, we kind of have competing things between their molar masses here and this relationship here. Okay, so it's a little bit more difficult to predict whether or not you should be getting a higher or lower mass in these cases. But just realize that it's really a balance between the difference in their molecular weights and their relationship inside of the equation. Let's try one more problem here. How many grams of O2 can be made from the decomposition of 100 grams of lead oxide? And we're given our equation for it. We have our given. We're given 100 grams of lead oxide and the equation for that decomposition reaction. We're asked to find the mass of O2. So our solution map is going to look like this. Remember that we need to go through the moles in order to figure out the proper ratios between the two reagents. We'll go through our relationships that we are going to need. We're going to need these molar masses of oxygen in order to go from the moles of oxygen to the mass of oxygen. And we're going to need the molar mass of lead oxide in order to go from its mass to the number of moles. And to go from the moles of lead oxide to the moles of oxygen, we need to know their relationship. That's coming from the formula that we have up here. We know that we're going to get 1 mole of O2 for every 2 moles of lead oxide. We get our relationships here, and then we string them together. After we're done canceling all our units as we go across, we see that we have mass of oxygen, and that we would get 6.689 grams of O2. When we do our check, we can again see that this is a complicated relationship based on the ratio between the two and the size of their molecular weights. But because the molecular weight of lead 4 oxide is much larger than the molecular weight of O2, we would tend to get a smaller number. Also, the moles are working against us here, right? We're only going to get 1 mole for every 2 moles of lead 4 oxide that we burned through.